Okay. Thanks everybody for joining us today. Today we're going to be bringing in a lot of topics that we've been talking about over the last 3 days. We've been talking about RAS, we've been talking about the fault management infrastructure. All these things have changed and are evolving, but one thing that stayed surprisingly static is what do we do in response to all this information? And when something goes wrong, how do we repair the machines? So this is a very important topic for us, and I'm glad that you guys have joined us today and are interested in it. So I have a couple people joining me today. I'm Dan Frame. I work on the Google team that's responsible for data center hardware testing, as well as manufacturing testing. It's my privilege today to be joined by Yuanlin, a tech lead manager at Google, as well as Richa Mishra, a data science technical lead at Meta. And in the audience, we have Mishra, who is basically the technical lead on the repair systems for Google data centers. Thanks, Ming. So he won't be presenting with us today, but so much of the content here that you'll see, we've worked with him closely on, and we really appreciate all the contributions that you've made to this. So what are we going to talk about today? Why is repair optimization important? What makes the problem difficult? And what are two common approaches to creating a repair strategy for a new hardware platform? And most importantly, how's the OCP test and validation track helping us solve this problem? As Drew said in another set just down the hall, we can only do this with good data, and the OCP Diagnostic format gives us the needed data we need to basically make actionable repairs. So why is the problem important? When customers come and move their applications to the cloud, they're expecting not only lower cost, they're also expecting greater availability. And when machines are offline, they're not contributing to redundancy. The CapEx and operational cost of machines continues to accrue when that machine's not serving. And most of all, downtime is expensive. You've got the cost of the repair. You've got the continuing depreciation of the asset that's not serving. And we also need to look at the average downtime for different machine types and incorporate that into our spare capacity modeling. If machines are down frequently, or machines are down infrequently but still take a long time to repair, we need to have more spare capacity. So in addition to those things, we have another problem that's happening. When I first started at Google 10 years ago, we had Gmail and we had Maps and we had the cloud, and all these were running on basically a fleet of very common hardware. All these machines looked the same. And as we've moved out into the cloud and customer workloads, that's no longer true anymore. And these static repair strategies that we've used in the past, they get harder to maintain as we have different types of machines. Now we have ARM, we have Intel, we have AMD, we have others coming up like RISC-V, right? And our architectures for these machines are starting to evolve as well. Each different machine configuration and type we have needs to have a set of spare identical or at least very similar machines that we can use to replace them. All of that adds cost and makes repairs more important for us. There's another even more nefarious side of heterogeneity, and that's that our most rare machines, the ones that we have the fewest of, they're also our most expensive. We need to repair those very, very quickly. These are running very specialized workloads. In addition to that, we also have scale out. You know, you've heard over and over that Moore's Law is over, right? I don't know if that's true or not, but I can say that we're certainly building more and more scale out architectures as opposed to scale up architectures. This is usually dedicated ASICs running generally ML or video acceleration workloads. And all of these scale-out architectures, they have more defect opportunities because they have massive numbers of interconnects, right? You can imagine if you've got something that looks like this, and you know, any picture that we show you is old, right? So what we have now looks even worse, and you can imagine how difficult it is to find a problem in this rat's nest of cabling. So what is a repair strategy? I want to frame this as an optimization problem, right? Anytime we have an optimization problem, we need a cost function. So a repair strategy is basically an attempt at finding an optimum minimum to the overall total cost of a diagnosis or repair of a defective device. The challenge of repair at scale is basically the same if you're doing it in manufacturing, whether you're doing it in the data center, or anywhere else, right? The cost of repair can be evaluated in different ways. Most typically, it's looking at the dollar cost of the repair or the time to repair. In manufacturing, there's other types of repair optimizations that we look at. It might be number of heat cycles on a particular area of the PCB that we're trying to optimize for. But all of these things, the math is the same. So what goes into a repair strategy? Generally, it's 4 types of information. We'll start with the historical information. What is the probability of a particular component failing in the first place? DIMMs fail all the time. Other components are more resilient. What has previously been repaired on the device? Like when we're trying to repair something, we don't want to swap the same thing 3 times. At that point, it's probably not going to work. The problem probably lies elsewhere, despite what the diagnostics are telling us. And we can look and say historically, what has fixed this type of problem successfully in the past? Then we have the test result information, and this is where the OCP Diagnostic standard comes in. If you're asking what's an OCP diagnostic, don't worry. We're going to be talking about that in the next 30 minutes right after this one. There are certain hard things in computer science, and scheduling is one of them, so bear with us there. But the test result information basically tells us what are the symptoms that have been observed to indicate that we have a problem? What components are failing at the same time or in parallel? And what do I know is working on the system? In other words, what do I have passing test for? What components can I say that have been exonerated? Then we have product information. That's how would a hardware expert recommend resolving this symptom if they were here and looking at the problem? How are these components connected together on the device? And what test coverage do I know I have? When I have passing and failing symptoms coming from my test, what hardware do they relate back to? And then finally, we have environmental information. This can be a lot of different things. It could be temperature, it could be location, it could be information about what are the common switches or common cooling components or common power domains, right? All of this goes into our repair strategies. So let's look at an example of generating a cost function for a repair, and I'll start with a really easy one. This one's just dollar cost. So if I want to find the dollar cost for a repair, I might look at the part cost, I might look at the cost of the labor, the cost of the downtime, and the overall cost to migrate or drain the machine, get customer workloads out of it so we can fix it and get it back up. All of those would be one particular cost function. But if I was looking at optimizing time to repair, you know, the coefficients may be different, but the algorithm's going to be the same. So in general, when we generate a repair strategy, there's 2 approaches that we've used. One is time-tested and true. I've been doing it for 25 years, right? These are rule-based systems, sometimes called expert systems, or when I got started, we called them debug trees, right? But this is where a hardware expert encodes their knowledge in a particular grammar. If CPU 0 is hot, then you first check the heatsink torque, then maybe you check the fan, then maybe you check the BMC, and then finally you check the CPU, right? These are the if-then-else rules. Now, we also have historical inference. And this model evolves in response to new evidence, right? Based on the test results and the historical data I have, reseating the CPU will fix the problem 89% of the time. I don't need to swap it. Maybe one example of what would come out of a historical inference system. So which approach works best? We've looked at it, and we feel that they both are synergistic with each other. On the rule-based system side, it has the following advantages. It's really simple and direct to understand. You can take your domain knowledge and you can tie it to repair logic very quickly. You can ramp these systems up pretty well. You don't need to do a lot of tuning, right? And they're straightforward to validate and debug. When you get a strange repair recommendation, you can go back and look at the rules and understand why that repair recommendation was made. On the downsides, they require incremental development for new symptoms and failure modes. One of the challenges that we have right now is we need to make sure that our diagnostics and our tests are in lockstep with these repair rules, right? If our diagnostics are generating symptoms that the repair rules don't address, we don't know how to remediate the problem, right? Furthermore, these rules don't work well due to the heterogeneity that I referred to earlier, right? As you have lots of different machines, it's hard to get common repair rules that work on them all. And with some of the technologies that we've looked at over the last 3 days, like CXL, things like that, where we're going to move to mesh fabrics, these problems are going to get more difficult. They're not going to get simpler, right? On the historical inference side, these evolve as more information is made available. These handle combinations of scenarios very, very well, and they automatically determine what is signal and what is noise from the symptoms and the data that we have. On the downside, when you don't have a lot of historical data, they don't work very well or they don't work at all. And sometimes you'll get repair predictions that it's not always clear on why that recommendation was made. And then you need to start going in to look at the model and why certain features were weighted more than others. So I mentioned earlier that I think both of these things, work well together, and this graph tries to illustrate that. you need the initial heuristics to kickstart the inference-based approaches. You need some data to work off of. But when that historical data sets become large enough, then inference-based approaches provide continuous improvement over and above that plateau. By applying both of them together, you can capture all this area under the curve, and all that is money saved. So why are repair rules so difficult to generate? It seems like it'd be easy, right? But it's not. This is a famous example. We've got one I²C primary device here and 3 secondary devices. In this particular case, I've got device C that's passing and the other 2 devices are failing. But what's really happening here is that device C has that bus in contention. It's got it locked. So it's not functioning correctly, but it's the only device that's passing. The other 2 devices are failing. They're working properly, but they're never able to get the bus, right? You can write repair rules for this, right? You can imagine what this would look like. You'd say if any one of them is failing individually, indict that part. If multiples are failing, maybe you now need to start looking at the passing part. But if you start to try to write that repair logic, and I've done it here just to show this one simple example, you can imagine how this combinatorial explosion quickly gets out of hand, right? You need some math to help you. So I talked a little bit about signal and noise. Our diagnostics and the OCP Diagnostic standard gives us so much information now. We have software errors, we have kernel logs, we have crash dumps, we have explicit test results that are tied to these events. So we can see what were we doing when this event occurred. We've got the execution times. We have all the parametric data that we've measured. This might be temperatures, fan speed, CPU loads, errors, BIOS postcodes, timing diagrams, all of that. It's all very, very useful signal for inference, and it's all notoriously difficult to write models or rules against. It's just too much information. So generally, when we do rule-based systems, we look at what the unhappy symptom was, and we try to write rules to repair that. Rarely do we try to use all this other information because it's just too difficult. So can you optimize these rule-based repair strategies? And you can, but it's difficult, right? One approach basically that we've looked at is simulated annealing. This is where you use Monte Carlo simulation. You kind of make random changes to your repair rules. And initially in the beginning, you allow bad decisions to be made where your repair rules get worse. And gradually, as you cool the system, as it's called in simulated annealing, you allow less and less bad decisions to happen, right? And what we're trying to do here is get out of this localized minimum where we might be able to find a more optimum minimum. The problem with this is twofold. One, where we go in and we simulate this, we don't know that our simulation really accurately captures what would have happened had we changed the repair rule. And the other problem is, if we try to do this in real life, our operation teams get very upset with us. They don't like making silly repairs to train models, right? They want to fix the problem and move on. So even though this works well in principle, it's very difficult to pull off in real life. At this point, I'd like to turn it over to Yuanlin, and she's going to tell you a little bit about how well our repair-based rule systems are working and some of the new inference-based approaches that we're looking at for repair prediction.
Thank you, Dan. Now I will give a case study on the performance of our rule-based repair system and introduce how we can use an inference model to optimize the hotspots. Google Data Center has used a rule-based repair system for more than 8 years. We start from hundreds of machine configurations to more than 1,000 machine configurations today. Currently, they share the same set of the rules to parse the test results and give repair recommendations. And now let's look at some analysis we performed on different machine configurations. The top right diagram, we compare the repair rate with the age of the machine configuration. We can see that the rate decreases on newer machines. Another study, which is shown in the bottom diagram, calculates the repair rate against the total number of machine configurations. We can also see that the rate decreases when we have a higher configuration count. The performance drop could be multi-causal, as in there might be a decayed test coverage. Some rules may need some adjustment, or in general, relying on granular symptoms alone to give repair recommendations is no longer sustainable as we have increasingly complex machine configurations. And now let's look at another case study we did on how the repair system performs against different test results. These are all the combinations our test can fail, where each circle represents a unique syndrome. In the image, the size of the circle represents how frequently the failure happened, and the color represents how many iterations we took to fix the problem. You can see that it's mostly green, meaning our rule-based system did a great job in general. But there are some hotspots we can improve. If we only look at the top 5 syndrome, 3 of them have some margin to be optimized, which give us more confidence that we are making a data-driven decision to start using and exploring an inference model. So what do we need to build a model? We know some information can be important, like test results, kernel logs, machine topology, telemetries. But as highlighted in the slide, too much data makes the model difficult to manage, and too little data makes them ineffective. We need a data structure to organize, categorize, and correlate those information for us. This is when we adopted the OCP Diagnostic specification. As Dan mentioned, there will be a deep dive presentation on this topic right after this one in the same room. So I will just briefly go through the schema, which give us essential data, not only for machine learning models, but also our rule-based repair system. The hardware and software details offer training features for machine learning models and branch conditions for heuristics. The diagnosis, verdicts, and errors are the core for most rule-based conditions, which can also be used as machine learning inputs. The parametrics and time series measurements can be used for anomaly detection and statistical process control. Now that we have the data structure, we start to build our training set. These are all the information Dan just mentioned. We need to interpret those data to a language that a machine can understand, which are numbers. For numerical attributes, like sensor readings, we just normalize them and use them directly. Other attributes can be categories, like CPU type. We encode them as enumerations. There are other granular attributes like the symptoms, which are encoded into Boolean features. For example, if we have a bad CPU verdict present in the test results, that feature becomes a 1. If it's absent, it becomes a 0. So let's look at how we sequence the model by first describing how humans root cause a test failure. We start from test results. Usually, after a brief look, we have an initial judgment whether it is a hardware or software issue. If it's a hardware issue and the verdicts point to the same component, we identify that component and send it to repairs. If the verdicts spread across multiple components, we check the machine topology to see if the reported components are physically or functionally connected. If they are, we send the root part to repairs. Now, if we still cannot find the broken component, we start digging into the logs, like kernel logs, machine events, console records, to see if we can find anything useful there. If not, we suspect our first judgment. Maybe this is not a hardware issue, which gets us to the lower part of the diagram. How do we triage a software failure? Tests can report an artifact called error, which describes software procedure issue. Similar to the hardware verdict, if the errors point to the same component or same package, or the reported packages have the same logical root, we identify the software component and reassign to the domain experts. Also, we all know that software issues can be tricky. If we cannot find the root cause from this one single failure on one single machine, we look at more test results on more machines to see if we can find any patterns from statistics. For example, if the failure rate has a big jump after a new release, we have more confidence that the new software caused the problem. And we can use the same strategy for environmental attributes. For example, if the failing machine all connect to the same switch, it's more likely that the switch, instead of any single machine, is broken. And similar to the hardware, if we cannot find the root cause from granular data, we start to look at the logs, the free format logs, to see if we can find anything useful there. If at this point, we still cannot find the root cause, we start to look at the time series information. For example, the health of the system daemons, or the CPU and memory usage, the sensor ratings. If we can detect anything abnormal when the test fails, we at least have a starting point to investigate. So in summary, we try to automate all the steps above. And this is how we divide and conquer. The red boxes here are machine learning models, and the green one is a data mining algorithm. We start from deciding whether it is a hardware or software issue, which is a binary classification. If we believe it is a hardware problem, then the issue becomes a multi-class classification to identify the broken component among all the components on that device. If it's a software issue, then we use some data mining algorithm to detect the anomalies and correlate them with the test failure. The last step is a time series anomaly detection model, which is used to find these suspicious patterns of a certain attribute against time. Each model gives a confidence score for each prediction, which we can use to rank the repair recommendations. You may have noticed that we haven't covered the free format logs yet. With that, I will introduce my friend Richa from Meta to show us how to investigate the non-structured data.
Thanks, Yuanlin. Hi, everyone. So going over, like Yuanlin mentioned, we are also trying to look at free format logs and how do we handle them when we are parsing at scale. Coming over, one of the main areas that we're looking at as part of OCP Diagnostics is having this process be able to enable the end-to-end flow for the categorization of errors. Error categorization is a key part of the NPI processes during hardware validation and testing. And this is one of the efforts that we are doing in parallel during the hardware design and hack phases during NPI. Here, the inputs are across different platforms, be it compute, storage, GPU, and across all of these platforms, we are running component-level tests, functional as well as regression tests. Once these tests go through different test frameworks, we are able to store the success logs as well as error logs into our test results data store. This data store serves as an input to the pre-processing step. The pre-processing takes into account all of the inputs that we get from the vendors, as well as our hardware SME leads who are working on the hardware validation phase. This helps us build the error category mapping config and serves as the source of truth that we're going to use for the overall mapping and categorization. This helps us build 3 different categories on a high level: tooling, platform, and levels. Tooling meaning automation or DC tooling, identifying hardware and software errors, and rack level versus server level errors. All of these feed into the post-processing processes where we're looking at categorized errors as well as uncategorized errors. The categorized errors directly feed into our UI where we're setting up thresholds for anomaly detection, and these are worked closely with our hardware SME leads. And the uncategorized errors then go into our machine learning platforms such as k-means clustering where we're doing unsupervised techniques, and the remaining are feeding into the natural language processing techniques. All of these together bring the pre-processing and post-processing steps in integration that helps us build the standardized format in order to look at the error categorization steps. Going over to the NLP implementation, this is an example for one of the error logs and how we would go through different steps within the NLP process. Tokenization, where we are separating all of these sentences into different tokens that would be of high significance when we are trying to come up with error categories. Stemming, stop word removals, and lemmatization in order to reduce any words that are occurring on a recurring basis and are not as significant when we are trying to find out or predict what the category should be. The POS tagging is helping us do the part of speech, so like noun, pronoun, and accordingly we can clean up the data further before we feed into a prediction model. And finally, the count word vectorizer, which is telling us how many times a particular word or a token is occurring, and based on that, we find out the frequency distribution. These are some of the steps that are going into the overall model, and we are currently deploying this using PyTorch, and given the scalability and maintenance, it makes it easier for further tuning. So finally, coming to the OCP Diag Parser, as Dan and Yuanlin mentioned, we are converging on the same standards in order to have the similar set of steps to be input as device metadata as well as test metadata within our test and automation framework. All of this also ensures that within the test step results, we add further categories for diagnosis, error objects, measurements, and logging, and helping us to understand how to structure the raw text into a standard OCP Diag structure so that this can be captured by other automated models. Finally, coming to the OCP Diagnostics and Inference repair model impacts, there are three main aspects that we are looking at here. We are providing a lot of investment into the repair heuristics, and like Dan mentioned, there is several cost factors that are going into this, and we are continuously working on improving these models, and this is helping us bring together both the hardware SME inputs as well as the state-of-the-art data techniques that can bring together more refinement in terms of our hardware debug process. Once these models are developed, there's also the operational efficiency improvements that are coming along with it as a byproduct, and these can help in increasing the overall effectiveness with which we are doing our triaging process. The model performance data is also providing us a feedback loop in order to recommend what type of tests do we actually have to run on our hardware in order to efficiently understand the performance at full load as well as at different operational stacks. With this, I'll hand it over to Dan to close us out.
Thanks, Richa. So call to action. If you're developing diagnostics like we are, and you distribute hardware that you want to go into hyperscaler data centers, adopt the OCP Diagnostic Output Specification. This makes your hardware plug and play for us, right? Bringing in the hardware is great, but bringing in hardware that's already productionized and ready to go and work with our repair systems is even better. The other point, which Drew picked on earlier, is all the hyperscalers have very large fleets and they generate enormous quantities of data to help you improve your hardware tests, right? The OCP format makes sharing that data back to our vendors and our strategic partners easier, right? If we have a problem that only occurs a very, very, very small percentage of the time, then you need lots of machines to find it. We can help you get that data. If you're passionate about this problem on the machine learning side, the diagnostic side, the test side, or maybe you just like fixing things, come join us. We meet every Wednesday at 8 a.m. Pacific time. We'd love to have you and talk more about this particular problem and some of the things that we're doing about it. I didn't talk very much about this talk because we have an hour of material and 30 minutes. But if you're using open firmware, we want to talk to you how you can leverage Redfish to provide some of the information that we need. We don't want to reinvent the wheel here. Redfish can provide a lot of the component connectivity information that we need in machine management telemetry, right? We want to be able to leverage that. Feel free to join us on our Slack talk here. And you can also go out and you can get reference implementations of the OCP Diagnostics here on the Open Compute GitHub repository. With that being said, thank you guys so much. I know we jumped ahead and we talked about an application that we're using OCP Diagnostics for, but if you're wondering what the heck are OCP Diagnostics, stick around and in now we'll talk about that. Thank you very much.